Hello, everyone. I'm Taekyung. I'm a software engineer at NVIDIA. I'm going to present Chakra. Chakra is an AI workflow twin for benchmarking and code design. So I started this project when I was a postdoc researcher at Georgia Tech working with Tushar, and we collaborated with Meta. And then I joined NVIDIA about a year ago. So in today's talk, I'm going to explain the basic idea of chakra, and also I'm going to explain how to convert these chakra traces into simulator form and run it into ASTRA-sim, which is a reference simulator. So please feel free to ask any questions, even in the middle of this presentation. So there are multiple requirements for AI software hardware co-design. And then these are the motivations that we had earlier when we designed Chakra. So let's say you want to optimize your system, like software system or hardware architecture. Then you need to understand the performance bottleneck. And also you want to explore the design space if it is a hardware architecture, right? So let's start from system software or system step optimization. Then you may need to understand the performance bottleneck. Basically in AI workload, overlapping computation and communication is critical. So you may want to understand the overlap between computation and communication. Then it means that you may need to run it multiple times, and also you need to analyze the overlap, right? But actually, running AI workloads on a real system is costly, right? You need a lot of GPUs. Of course, I'm from NVIDIA, so it is definitely good for you to buy more GPUs. It is better, right? More GPUs you get, you can get more performance. It is better. But anyway, your budget is limited, right? So you need to replay it. Running workload multiple times is costly, right? Instead, as AI workload is repetitive, you can take just one iteration of your AI workload and record the communication and computation behavior, and then you can just replay it to understand the behavior. And also you can adjust your topology or network bandwidth to understand potential performance gain, right? That is the first motivation. Let's say you want to design GPU or any kind of other hardware, right? Then you may want to explore the design space. But the important part is to feed the realistic workload trace. You cannot just randomly describe the behavior, right? Ideally, you should collect your behavior, the workload behavior from real workload, right? And Chakra allows you to collect traces from real workload, like PyTorch workload. So that was the second motivation. And also you need to analyze the performance bottleneck, as I mentioned, and also you need to understand the performance gain that you can achieve, right? And also we need to share these traces between software companies and hardware companies. So software companies understand the behavior of workload, but actually hardware companies have limited information about the software behavior, right? Then it is better for us to have a shared common schema for us to share the traces. And also it is important to redact any confidential information from these traces. So these are the key motivations that we had when we start this project. And then we came up with this idea about chakra execution trace, and we wanted to express any kind of ML workload behavior with graph. And chakra execution trace is basically a graph, and the graph is designed for describing the behavior of our workload. And it depends on how you want to model the behavior. And in this chakra execution trace, we first model with some simple assumption like there must be some computation operators or communication operators and memory operators, and there must be dependencies. That's how we started, and then we developed the schema. And this allows us to remove any confidential data. So as it is abstracted format, it does not have any user data in execution trace. And also, depending on the use cases, if a software companies or any trace provider wants to remove any confidential structure, then they're allowed to do that, right? But they may lose some ability to model the actual behavior, but they're free to do that. And also, it is very helpful for us to model a system behavior at a higher level. So collective communication can be modeled with peer-to-peer send and receive, but in this case, the trace size will be very, very large, right? Instead, we can just make a single node for collective communication in this chakra trace, and we can let the simulator to model the collective communication. So we can have this kind of flexibility in performance modeling, and also it is good for collaboration for hardware software co-design. So yeah, as Tushar mentioned, this is part of ML Commons. You're free to contribute to this chakra execution trace and code base. And we have bi-weekly meetings, and we have a working group, and we have a shared drive for discussion and so on. So you're free to join. Okay. This is the concept of about chakra execution trace. So yeah, this is the chakra ecosystem. We can collect chakra execution traces from AI workload. So you can collect chakra execution traces from PyTorch-based ML workload. And also, if you just modify any existing platform, then you're free to collect chakra execution traces. Currently, we support PyTorch. And then you can convert these traces into simulative form, and then you can simulate any kind of future architecture with these traces. And you can use ASTRA-sim if you do not have any internal simulator. If you have internal simulator, then you can adapt your simulator to feed these traces and run performance models. And also, as I mentioned, there is another flow called replayer. And then you can replay chakra traces on a real system. And there are other toolchains in ML Common Chakra. So ML Common Chakra repository is an open source project. So you can find all tools available on GitHub. And then there are other tools like synthesizer, analyzer, and visualizer. So synthesizer is about synthesizing chakra execution traces. And one of the PhD students in Tushar's lab is working on synthesizing chakra execution traces. So the idea is to synthesize traces based on a predefined behavior. And then it allows us to share some behavior without revealing any confidential data. And visualizer is about visualizing the execution. We can generate timeline from simulation. Okay, so let me introduce the chakra execution trace schema. And this chakra execution trace schema is available on GitHub. And then it is defined in the protobuf format. Let's start with node. So as I mentioned, we have abstracted away the detail with node. And in node, you can find unique ID that will be used for uniquely identifying the node. And also you can find the name, it is not unique. And also there is a type field. And you can find the type field here. And there are multiple types like invalid node or metadata node or memory load, store, computation, communication, and so on. So this is what we have for type. And there are control dependencies and data dependencies field. And I'll explain these kind of dependencies in the following slide. And then we have fields for timing, like when does this operator start? And also what is the duration of this operator? And then we have inputs and outputs field to describe the input and output of this operator. And the input and output can be tensor or integer and so on. And we have attribute field, and it is a repeated field. And this allows us to encode any kind of data for this operator. And this is the defined as attribute proto. And attribute proto has name and docstring field. And it has another field called value. And value is defined as one of. and it can have one of these values, like double, it can be double or float or double list or float list and so on. So for example, let's say you want to encode additional data. Let's say it is like flops for a compute operator, right? Then you can add a new attribute called flops, and you can set the name as flops, and then you can set docstring, but it is optional. And then let's say flops is just int 32, then you can set this number, right? Then you can encode such information in the node, and in your simulator, you can decode this information and use it for performance estimation. So that is the basic idea of chakra execution trace. And then also you can use this kind of approach for any other purposes. So this is how we collect chakra execution trace. And actually, there are multiple stages that we can collect chakra execution trace. So this is how we convert AI model into the final execution. And first, there is an AI model on the left, and then it will the ML framework like PyTorch will perform multiple transformation like platform agnostic transformation or platform dependent transformation and so on. And there can be at least 2 points to collect traces. One is pre-execution trace, where platform dependent transformations were not applied. And the other is post-execution trace, where all transformations were applied. So currently, I am talking about post-execution trace, where all the transformations were applied. But we are also exploring the other option, pre-execution trace. And pre-execution trace, one of pre-execution trace is FX graph. Yes, so one of PhD into Charles group is exploring this space. But anyway, I'm going to explore post-execution traces. So let me explain how to collect chakra execution traces. So actually, there are multiple types of chakra execution traces, but the main type is chakra host execution trace, and it is also called PyTorch execution trace. And the other type is chakra device execution trace, and it is also called kineto trace. So all you need to do is just to add a profiler. For example, let's take a look at chakra host execution trace profiler. Then you need to instantiate execution trace observer. And then after that, you have to register callback. And when you register callback, you have to provide a file name. And the file name is pytorch.et.json. And then there must be multiple iterations in your AI workload. And then you can start profiling by calling et.start. And after collecting traces, you can call et.stop. And then at the end, you can just call et.onRegister callback. You can do the same for chakra device execution trace. And this is the profiler code. And I explained the details and differences between these two types of traces in the following slides. But anyway, this is how you can collect chakra execution traces. And we have a wiki page for collecting chakra execution traces and simulating on ASTRA-sim. So you can take a look at it. There is a wiki tab in GitHub repository, and then there are other useful links and documents, so you can take a look at it. Okay, so this is an example of chakra host execution trace. And first, when you collect chakra host execution trace from PyTorch, then it will be in JSON format. And then you can find a global metadata, as you can see here, like schema, PID, time, start time stamp, and so on. And also you can find list of nodes. And then in the node, you can find the metadata that you need, like name, inputs, ID, RFID, parent, and so on. Okay, you can collect chakra device trace as well. And this is the chakra device execution trace example. And this is also in JSON format. And also you can visualize the device execution trace with Chrome tracing. Okay, I have explained chakra host execution trace and device execution trace and how to collect these traces, but I have not explained the details and differences between them. So This is partly because of the implementation in PyTorch, the profiler implementation and how these two traces developed independently. But anyway, that's why we had these two types of chakra execution traces, but you need to understand the differences. So chakra host execution trace is also called PyTorch execution trace. And in PyTorch execution trace, you can find operators, and the operators are CPU operators. And GPU operators are generated or called by CPU operators. So GPU operators do not appear in chakra host execution trace. On the other hand, in chakra device execution trace, you can find CPU operator and GPU operator at the same time. So this is an example of visualization of chakra device execution trace. And you can find CPU row and GPU row, and you can find two processes like Python, thread 1 and thread 2, and stream 7, stream 20. So you can find CPU operators and GPU operators at the same time in chakra device execution trace. And another important difference is the dependency. In chakra host execution trace, you can find control dependency and data dependency. So you can just think that in chakra host execution trace, dependencies can be presented as graph like this, with arrows and the nodes and so on. But in chakra device execution trace, they're presented as a timeline with start time and duration. And another important difference is that chakra device execution trace will have more information about GPU operators like GPU metadata, the number of streams, and the kernel type, and so on. So this is the differences between these two types of traces. And yeah, this is the visualization result. And okay, I think this can be a little bit complex, but let me explain. So there are two types of dependencies in chakra host execution trace. One is control dependency and the other is data dependency. So data dependency is just data dependency. Let's say there are two operators, and the second operator, if the second operator takes the output of the first operator, then there is data dependency. And control dependency is considered as a kind of call step. So let's say we have a function like this. This function calls empty, barrier, or reduce, record param comps, record param comps. Then these 5 operators will have control dependency to this method. So this is the concept of control dependency in chakra host execution trace. And it can be visualized like this. Okay, so I have explained chakra host execution trace and chakra device execution trace. But to run a simulation with chakra execution trace, you need both information. You need dependencies between operators, and also you need GPU operators, and also you need GPU metadata, right? So in the end, we need to have structured dependency information, and also we need to have timeline information like the duration of operator or GPU kernel information, and so on. And then we have implemented the toolchain to merge these traces into simulatable chakra execution trace. And I'm going to explain the procedure to merge these traces. So we have implemented these tools about since 2022. And then we have working toolchain. Of course, there are some corner cases that we cannot cover, but with this toolchain, we can achieve pretty high accuracy when we replay. When we just reuse the measured time, then we can achieve like 90% or 90% accuracy. Of course, there are other corner cases that we cannot cover right now, but yeah, it works pretty well. And the code quality is not bad. So actually, it is better than a year before, so you can try it out. Okay. And this is the flow that we need to follow to simulate execution traces. Okay. First, you need to collect traces from a PyTorch model. And then you can have two kinds of traces. One is chakra host execution trace, and the other is chakra device trace. And then, as I mentioned, each have advantages and disadvantages. So we need to merge them into a single trace, and it is called, the result is called chakra host plus device execution trace. And all of these three traces are in JSON format. And then we need to convert the chakra host plus device execution trace into the final form, post-process chakra execution trace. And this chakra converter is responsible for converting JSON schema into protobuf schema so that we can feed it into ASTRA-sim. And also it is responsible for converting control dependencies into simulator dependencies. And then let me explain the steps to process these traces. Okay, let's start with trace merger. So I'm going to explain these steps at a higher level, but if you have any questions, then you can ask me, then I can answer them. But anyway, so when you merge these traces, then there must be at least two types of operators. One is CPU and the other is GPU. And you need to connect CPU operator to GPU operator in the merger. It is because chakra host execution trace has CPU operators, but it does not have corresponding GPU operators. So what we do in the trace merger is to instantiate GPU operators, and then we find the corresponding CPU operator with event ID or by looking up their start time. And then we can correlate CPU operator and GPU operators. That's the first step. And also we need to understand the actual execution time of one operator. So when you take a look at the timeline that we had earlier, so it can be broken down into multiple levels. And in the end, we need to find out the exact duration of a single operator. But actually, a single operator may call multiple children operators, right? Therefore, we need to exclude all children duration, and we need to find out the exact duration of the operator. That is the next step that we need to do. And also, there can be some dependencies between threads. So when you just visualize the kineto trace, then you can find two threads or three threads and so on. And there are some implicit dependencies between threads. And you need to introduce such dependencies in the chakra host plus device execution trace. And also there can be, there is inter-stream dependency. If a GPU operator is executed in a specified GPU stream, then the GPU operators in the same GPU stream should be executed in the order. So that is intra-stream dependency. Okay, currently as I mentioned, there are operators with in chakra host execution trace, and also you can find operators in chakra device execution trace. But the problem is that they have different, they're in different trace format, and they're in different files. You need to find a corresponding operator. So let's say you have CPU operator A in chakra host execution trace, and let's say you have chakra host execution chakra host operator, CPU operator A also in kineto trace, chakra device trace. Then you need to correlate these operators, right? So it has to be done in the trace merger as well with operator matching. So that's what we have done in trace merger. And then let's move on to chakra converter. So I explained the concept of control dependency. Control dependency is a kind of call stack, and let's say ID2 calls ID3, 6, 7, 8. Then ID3, 6, 7, 8 have control dependency to ID2. That is the concept of control dependency. But actually, when we run a simulation with chakra execution trace, then we need to convert these dependencies into a specified order, right? So usually in a simulator, when you issue an operator, then and the operator is completed, then dependent operator should be issued, right? We need to convert control dependencies into simulatable dependencies. That is the main role of chakra converter. And also it is responsible for converting JSON into chakra prototype format. So this is the control dependency that you may find in chakra host exchange trace. And after conversion, it will be converted into a simulatable dependency by running DFS. And yeah, that is the concept of dependency conversion in chakra converter. But anyway, so this is the internal of chakra merger and converter. So as long as our implementation covers your use case, then you don't need to know about all of the internals. But anyway, you can just collect chakra host exchange trace, chakra device exchange trace. To do that, you need to add profilers, just merge it, convert it, and then fit it into simulator. Then you can find the final result. And yeah, that's it. So this is the internal of about chakra converter. And then there are other tools, as I mentioned. There is a replayer tool and visualizers and analyzers. For analyzer, I would recommend you to take a look at holistic trace analysis. It is developed and maintained by Meta, and you can feed chakra device execution trace, and then you can break down the execution time. As far as I know, Meta is using it. Let me see. Okay. So your question is about the availability of traces so that anyone can use it, right? So as far as I remember, there were some setup traces that were accessible to the public, and it is still accessible, but the environment is still evolving. So we do not have the latest set of traces right now, but yeah, let's see. Tushar.
Yeah. I mean, so we did have a set of traces, and like I think folks who are in the working group, like a Google Drive, they're not kind of robust enough to be released publicly yet, but there are some traces. Good question. Yes, so that's the different. Yes, so there are also mechanisms to synthesize traces, and we talk about that as a thing. So there you can potentially synthesize for arbiters. Yes. But for some of the real systems, I think we've been, as you said, I think we've been trying to kind of encourage a lot of the members to kind of contribute the traces. I think Meta right now is involved a lot in maybe just making sure that the whole trace collection flow is clean. So that's been their effort, but eventually we hope that they'll be able to contribute. At Georgia, we've also been collecting some traces of some we have. The hope is to get them on.
But it eventually evolved, so like Meta did their Mama 3.0. They were able to distill down to say, hey, this is really kind of we can simulate enough of this on say then we can extrapolate some of the knowledge.
Yes, so that's another kind of thing we've been trying to do, which is more of maybe comes in the analysis where like take a bunch of traces and together, try to come up with a representative trace that has enough of that information. That involves a little bit more statistical analysis. I think that's a little bit more of a research that's been going on. The other things are more like this is the trace.
Okay. Okay. Actually, that's it for the chakra section. So, do you have any other question regarding chakra? Okay. Okay. So you're at. Hmm? So the publicly available simulator is ASTRA-sim. It is a reference implementation. And as far as I know, many other contributors are interested in using chakra execution traces.
Yes. working group, and I believe they are using other simulators. So I think it's been a different model. For example, I know we have it talked by AMD, right? So there's some companies that have, let's say, kind of leveraged the front-end part of ASTRA-sim but plugged in their own internal models. While there's others who are like not even using ASTRA-sim, just take Chakra and feed it to their internal. So I think there are a few companies that have been.
Maybe use the wrapper for the ASTRA-sim and with the thing.
So it depends again on what, like, I think for some people who, like this is an example, right? Like if somebody is just interested in a network simulator and they want to leverage ASTRA-sim for all of the connective communication, what it has, that's done. But I think there's others who, they have their own internal simulators they were already using for whatever, and they just, and now this becomes a mechanism for them to get a more representative workload and just leverage the converter and kind of the leverage some of the public code base on. So you can kind of see the code base that on how to feed the traces into ASTRA-sim and kind of use that as a reference example for feeding traces. So there are a few companies that have been doing it. I believe Keysight is a member of the working group. I think they use their own simulator, from what I understand. Scala Compute uses their own.
So you
Yes.
can easily replace your front end of your simulator if you already have a simulator. We have ET feeder. So it is a feeder to feed Chakra execution trace into your simulator. So anyway, when you want to integrate any other component in your simulator, then you may need to put some efforts, right? Like, for example, if you want to integrate more sophisticated memory model, then you may need to convert the request generator and interface and so on. And you can do the same for Chakra execution trace. So for example, if you have any kind of front end for your simulator, then you can just replace it with ET feeder. Then internally you can have access to the classes and so on. And you can find other tools as well.
No, it was, I think, the other way around. I was saying that they.
I understand
Yeah.
that the
Yeah. Good question. That's my. Good. Yeah, that might be a question for them. I think it's
Is there, okay. Okay, so it is a little bit quite blunt statement. So let me explain the detail. So Chakra execution trace is just a graph, right? And in the graph, we have operators like compute, communication, and their dependencies and so on. And if you want to simulate the future architecture, then you need to have a performance model in your simulator. It can be any performance model like a roofline model or anything else, or estimator, right? But for validation, I just used the measured duration from an actual workload run. And then for each operator, I can find the execution time of an operator, right? Then we have a dependency graph with duration, right? And then you can just simulate the graph without running a performance model, right? Then you will have the execution time of a graph, of a given graph after running simulation, right? That is the result of the simulation that I was talking about high accuracy, like 90 or 95%. And I compared that result against real system measurement. For real system measurement, we can use kineto trace, Chakra device execution trace. So when you collect execution trace, then there is Chakra device execution trace, and it is actually timeline, right? Then you can just click. You can just click it. Then you can find the duration of your profiling step, right? That's what I have done. But when it comes to simulating the next generation architecture, then it depends on your performance model, right?
Yeah, they just kind of put it to explain the case as you said, like what's the graph itself. Why would there be a difference from the real system? Is it because some operators were not captured?
So let me see. I think some delays, some implicit delays are just removed. When you take a look at it, then there are some other delay gaps here, right? This kind of delays may be ignored in the final simulatable execution tree. Maybe that is the reason. Okay.
The tag that you created and you have the individual timing of the operators and then depending on the rest doesn't matter, it just has to load the future part. And then you add it up to that. That's where you were having about a 5% black.
Sorry.
Yes.
Yeah.
I think it's
Yeah.
what you said. It's the fact is the two approaches are, one is you collect the trace and you have the time, like literally the time from Kineto or how long it took. Versus you took the trace, simulated each of the operators through the dependence, and again, whatever the longest dependence is, that will kind of become the critical part at that time. Right? I
Yeah,
think those- that's the-
yeah, kind of. And there are some other corner cases that we cannot cover right now. So yeah, it is still ongoing work. Okay. Over there. Actually, yeah. No. Okay.
So you can obfuscate the value of the data structure, but your graph can, the control flow graph can still reveal.
Yeah. Yeah, so let me explain. Based on my understanding. So it is still ongoing work by Tushar's group. So there are multiple levels of obfuscation. So by default, when you collect Chakra host execution trace from Python, then anyway, you do not have user data, right? That is one kind of obfuscation. But still, Chakra host execution trace may have some information about communication pattern and computation pattern. Then we may still have some confidential data, right? Then another solution to redact this confidential information is to generate traces, right? But we need to find a balance between confidentiality and modeling capability, right? So if you do not want to reveal anything, then you cannot model it, right? So another solution that was done earlier by Meta is generating traces. So there were multiple versions of generating traces, and the first version was already presented at the Chakra working group, and I can explain it. So let's say you want to have Chakra execution trace that model the communication behavior of your workload, right? Then you can collect all of the traces and you can find the pattern, like the distribution of your collective communication, like all gather, all reduce, and so on, right? And you can find the distribution. And also you can find the pattern in job size, like the number of ranks, right? And also you can find the pattern between collective communication. I'm just talking about communication because they've just focused on communication, right? Then you can have multiple stages of distribution generator, and then you can just generate traces. It does not have to be very accurate. I mean, it does not have to be very detailed like computation and communication. It can just have a pattern of your operators. Then you can just simulate it and replay it, right? And currently, Tushar's group is exploring some more complicated model. It is called Trace GPT, right?
The high so like instead of using the actual traces, have a model that can use those traces and like spit out some other, and so that trace is representative, but then it will not. That's kind of the issue. But as taking, I think that is that part is also kind of more work in progress and more researchy.
Granular stress, let's say, right?
So actually, the
Yeah.
next part of the talk is literally on that. So I think that
Yeah.
might answer it.
Yeah, I think so. Yeah, and if it does not answer your question, then you can ask a question again.
Generate some models for mixture of experts.
Yes, so we can do that as well. So that's as long as a model is in PyTorch, like we can and I think in the demo session we will talk about that. We collected traces from Mixtral and so on.
How do you deal with overlap? Nodes in the day. I mean, when Tushar talked, he talked about overlap to compete. How do you deal with that?
Okay, so you can first you can express the dependency and parallelism in the graph. So if two operators are not dependent, basically they can be executed at the same time, right? Let's say there is a compute operator and there is a communication operator, then they can be executed in parallel in theory, right? First, it should be expressed in execution trees, and in your simulator, you are responsible for running or submitting these operators in parallel. And yeah, that's what we have done in ASTRA-sim. Thanks. Okay.